Now, let's take a look at example 2. A farmer has 600 meters of fence, and he wishes to enclose a field beside a straight section of a river on his property. For practical reasons, the length of the sides of the field should not be less than 50 meters. Find the dimensions of the field so that the enclosed area is as large as possible. Fencing is only required on 3 sides. In the diagram, we can mark off the 4th side that doesn't require fencing, and then we can let X and Y to represent the length and width of this area. Since there is a total of 600 meters of fencing available, we can say that X plus 2Y is equal to 600, and the length of the sides should not be less than 50 meters. So we can say that X must be greater than 50, and so is Y. Also needs to be greater than 50. Let's get rid of this mark. Okay. So you may have noticed there is a pattern when we are dealing with these optimization problems. Usually we need one relation that will allow us to relate the variables involved, and then we will isolate one of these variables so that we can substitute that into a function where we can actually minimize or maximize the quantity that we're looking for. And in this case, this is a maximizing area question. So it looks like I can easily isolate X in the expression. So X is 600 minus 2Y. Because of this, I can use this relation in setting the boundaries for my variables. So 600 minus 50 is 550. That's greater than positive 2y. So here, if I divide both sides by 2, what do I get? 2 is 1575, right? And putting the boundaries for y together, this is telling me that y is less than 275 but greater than 50. So in total, it will be 50 less than y less than 275. That's what we're going to aim for. So next, we're going to set up the function where we're going to maximize the area. So the area formula is very simple. It's x times y, length times width for a rectangle. Let's write a in terms of y, since we have x equals to 600 minus 2y. And area is equal to 600y minus 2y squared. Okay, so now we're ready to do the important step, which is to differentiate the area, this time with respect to y. So here we have 600 minus 4y. Set this equal to 0. I have 600 minus 4y. In other words, y is 150. Notice how you can use your judgment to see if your answers make sense. In this line here where we have a function of area in terms of y, this is quadratic. And we know that in a quadratic function, there is only one maximum or minimum point. And in this case, because y squared term is negative, we know that the parabola opens down and you have a maximum occurring at 150. Since we do have a boundary for y, to make a t-chart where we have to actually test out which of these y values will give us the maximum area. So the lowest bound is 50. We found that there is a turning point at 150, and 275 is the upper bound. Okay. So when you do this calculation, I believe you're going to get 25,000, 45,000 for area, and 13,750. Okay. Indeed, using this chart, we know that this is the maximum area. In other words, we can now work out the length of x by substituting y equals to 150, okay? So x is 600 minus 2y. Oh, yeah. So now let's sub in 150. So that's 600 minus 300. That's 300. Therefore, the maximum area is given by a field with dimensions 150 meters by 300 meters. And this is example 2. So let me shrink this page and move on to example 3, which is slightly different. So let's read the question. Cost in fuel per hour for a ship is twice the square of the ship's speed in water. Oh, that's complicated. If the adverse current is 5 kilometers per hour, find the most fuel efficient speed for a ship required to make a 100 kilometers journey. Okay, so this is very wordy. There's a lot of information given. Usually I like to, set aside some time to analyze what's really given to me. So the cost in this question is twice the square of the ship's speed. So if we let the speed to be v for velocity, then cost per hour is equal to 2v squared. We want to find the most fuel efficient speed, v, but this means that we try to lower the cost, right? We want the lowest cost. And the journey in total takes 100 kilometers. And no matter how fast the ship can move at, there is an adverse current that goes against it at 5 kilometers per hour. So thinking about what we know about, distance, speed, and time, we know that speed is distance over time, or however way you remember this formula. So it seems like the total cost is related to 2v, the actual cost per hour, multiplied by how many hours the journey takes, right? So combining what we know, I think it will be ideal for us to rearrange this formula and say, well, the total time that it's going to take to complete this 100 kilometers journey is 100 kilometers divided by the speed of the ship, the actual speed. So the ship is traveling at v kilometers per hour minus 5 kilometers per hour. Does that make sense? So it looks like we can now say that the cost function looks like 2v squared times 100 over v minus 5. So let's try to simplify this function first, because I have a lot going on. Okay, so this is 200 v squared over v minus 5. That's c. So if I take the derivative of this, it looks like I can make use of the quotient law. C prime. So take the derivative of the top part, 400 v times the function in the denominator, minus the derivative of the function in the denominator, which is just v minus 5. Derivative is 1, 200 v squared multiplied by that original. And then this whole thing divided by the square of v minus 5. Okay. Setting this equal to 0, I can expand and simplify the top part as well. I get 400v times v, 400v squared minus 200v squared. That's 200v squared minus 2000. Okay, my v doesn't look good here. Okay, 2000v over v minus 5 squared. There was a better way to do it, but that's okay. So let's factor this. Yeah. The denominator, in a sense, is irrelevant other than telling us that the fact that v cannot be 5, right? So we get v equals to 0 or v equals to 10 in this case. But if you have a v of 0, the speed is 0, that means the ship is stopped. That doesn't make sense. As a result, the most fuel efficient speed must be 10 kilometers per hour. I hope you have learned something about optimization in this lesson, and you recognize that there is actually a structure to solving these problems. And now is your time to practice by doing some homework questions.